Well, so this is the last class we are going to have in the course on phase equilibrium thermodynamics. Till now we have had a large amount of discussions on vapor liquid equilibrium solutions for different systems. Now, for all these systems we found that vapor liquid equilibrium phase diagrams and the equations for both ideal and non-ideal solutions, they cover a wide range, and this is primarily important for the design of distillation columns. Now, apart from distillation, there are also large number of other mass transfer operations, and I felt that a small or a brief discussion regarding the phase equilibrium relationships which govern the other mass transfer operations, if they are not at least touched upon, the topic of phase equilibrium thermodynamics remains unfinished or incomplete. So, therefore, in the last class I have decided to touch upon the phase equilibrium relationships which are important for other mass transfer operations. The phase equilibrium relationships other than vapor liquid equilibrium data, which is important for distillation columns. Now, let us see what are the other mass transfer operations that usually a chemical engineer deals with. Definitely distillation, we know that the principal underlying distillation or the mechanism of separation which is used in the distillation processes is that it exploits the difference in volatility of the two components to be separated. Apart from distillation, we have absorption and stripping. What happens under this case? There is a gas phase, we bring it in contact with the liquid, and the liquid absorbs the gas from a mixture of gases or from a pure component gas. A most common example is the absorption of carbon dioxide or sulfur dioxide using sodium hydrocaustic soda or caustic potash solutions. Now, in this case also we cannot have the complete absorption, or maybe suppose we have some amount of sulfur dioxide or carbon dioxide, there is a limit to which this gas can be absorbed in the sodium hydroxide or any other solvent that you use, and the maximum amount of absorption that can take place, that depends upon the equilibrium concentration of sulfur dioxide in the caustic soda solution or any other solvent that we are going to use, and this is governed by the solubility of that particular gas in the solvent that we are going to use. Naturally, since sulfur dioxide is more soluble in caustic soda solution as compared to water, so definitely we will have a greater separation or a greater purification of the gas phase if we use caustic soda solution in place of water. So, this is governed, or the process of absorption is governed by the difference in or rather by the solubility of the gaseous constituent in the contacting liquid phase. Now, in stripping, the mass transfer occurs in the reverse direction. In this case, mass transfer occurs from the liquid to the gas phase or the vapor phase, and in both absorption and stripping, since it is a mass transfer between a gas phase and a liquid phase, both of them they depend upon solubility of the gaseous constituent in the contacting liquid phase. Accordingly, the equilibrium relationship in this case is the solubility of the particular gas in the liquid under constant temperature and pressure conditions. And naturally, if you are dealing with solubility of the gas, it is quite natural we will be more concerned, the mathematical equations which will be governing this is the ideal dilute solution law, the Henry's law, in contrast to Raoult's law which used to govern vapor liquid equilibrium for distillation cases. There is another mass transfer operation which we have, which is known as extraction. In this case, what we have, we use a second liquid phase to extract any particular component from one particular liquid phase. For example, suppose we have acetic acid in toluene, we would like to purify toluene, or we would like to remove acetic acid from toluene. We use water, we bring the two phases in contact, and we try to purify toluene from acetic acid to the maximum extent possible. Now, what is this maximum extent? Definitely it depends upon the relative solubility of acetic acid in toluene and in water. So, therefore, in extraction we find that the mass transfer between the two immiscible liquid phases, it depends upon the preferential solubility of the desired component which is to be separated in the two liquid phases. Then we have another mass transfer operation which concerns solid liquid or solid gas mass transfer, that is known as adsorption, and the reverse is leaching. In adsorption, a solid phase, it adsorbs either a gas or a liquid phase, and in this case naturally the mass transfer is governed by fluid solid equilibria, and in leaching the mass transfer occurs in the reverse direction. Now, for all these mass transfer operations, what do we need to do? First we need to create two phases, and then we need to have mass transfer between the two phases. How do we create the two phases? For distillation, we find that creation of the two phases is just by heat. We have the components in the liquid phase, we apply heat, we have a vapor phase. Naturally, the vapor phase is richer in the more volatile component, the liquid phase is richer in the less volatile component, and we keep on contacting them and separating them and again contacting them. In this process, the liquid progressively becomes richer in the the less volatile component, the vapor becomes richer in the more volatile component, and in this way we can get a substantial good amount of separation. In absorption, leaching and extraction, we find that we need, in fact, apart from distillation, for all other mass transfer operations, we find that we need a third component in order to create the same phase, or rather in order to create the second phase. Unlike distillation, where the contacting vapor and liquid phases are derived from the same source, for all other mass transfer operations, a third phase is required in order to effect separation. For example, in absorption, leaching and extraction, this third phase is the liquid phase created by introduction of a liquid stream. Liquid stream is often termed as the absorbent in absorption, or it is termed as the solvent in case of extraction, leaching, and also in absorption we often call it as a solvent. In stripping, the third phase is an external vapor stream, which is often referred to as an inert stream, and in adsorption it is the adsorbent contacting, it is actually the solid phase which creates the adsorption. This is wrongly written, this should be the solid phase which creates the medium where the liquid or the gas is preferentially adsorbed. Now, in all these particular all these mass transfer operations, we find that for separation of a binary mixture, for distillation the minimum number of components is 2, and for all other operations it is 3, and for all operations the number of contacting phases is 2. What are these two phases? For distillation or rectification, it is the vapor and liquid phase of the same components. In absorption or stripping, it is a gas phase and a liquid phase. In extraction, it is the two immiscible liquid phases. In leaching, it is a solid and a liquid phase. In adsorption, it is either a solid liquid or a solid gas phases. Now, for all these phases, again the way I had told you, the first thing which we need to do is to create the two phase system. I have already discussed how we create the two phase system. In distillation, it is created by heat. For all other cases, it is created by a addition of a third component. Then we have to effect mass transfer between the phases. Once by mass transfer separation occurs, then we try to separate the two phases. Now, this mass transfer, this is governed by phase equilibrium. We cannot have as much mass transfer as we need, and the mass transfer under constant temperature pressure conditions, it is limited by the phase equilibrium considerations, and this phase equilibrium is denoted in different ways for different mass transfer operations. And just like we have already discussed, we can have graphical representations of phase diagrams, and we can also have mathematical equations for the phase diagrams. Remember, for all phase equilibrium problems, the governing equation is the same. What is the governing equation? For each component I, the chemical potential in phase alpha and in phase beta have to be the same. This alpha and beta, they can be, maybe one is a gas phase, the other is a liquid phase. Both of them can be two different liquid phases. One can be a solid phase, other can be a liquid or a gas phase. Whatever be the case, the condition of thermodynamic equilibrium remains the same. It is the equality of chemical potentials of each component in the two phases. And therefore, how do we develop mathematical equations? For developing mathematical equations, we try to express the chemical potential of each component I in the two phases in terms of the compositions of component I in the corresponding phases. And those particular equations, when they are equated, we get we get phase equilibrium relationships. Now, tell me, for absorption, what is the standard equation? For absorption, as I have mentioned, the ideal dilute solution, or in other words Henry's law, is the governing equation in case of absorption. For adsorption, if we see, for adsorption, the basic equation, the simplest equation, it is of the Henry's law type, where the equation is given as Q equals to A into C star. Now, the first question is, what is Q and what is C star? So, well, Q, it is the, naturally for adsorption, it is a solid phase as well as a liquid or a gas phase. So, Q, it is the amount of solute adsorbed per unit mass of the adsorbent, that is the amount of solute which is adsorbed. It can be a liquid phase or it can be a gas phase which is adsorbed per unit mass of the adsorbent, and C star, it is the equilibrium concentration of the solute phase. The C star, it is the equilibrium concentration of the solute in the mixture. That means, in the gaseous mixture, if it is a gaseous mixture, then a conventional way is to express the concentration in terms of partial pressure of the gas. So, therefore, usually if it is a gaseous mixture, then we prefer to replace C star with Pi star, and if it is a liquid mixture, then we express it in terms of concentration, where the concentration can be either in terms of weight per unit volume or weight per unit weight, or maybe moles per unit volume, etc., etc. Now, in this case, we find for absorption, while the Henry's law was the most common equation, or it is the ideal equation which is used. We have already discussed Henry's law, and in this particular case, I will just write down the equation for your convenience once. It is the Pi star equals to Hi Xi, which you already know. Well, there is one thing I think which I should be mentioning before I proceed further, that is the different units in which the concentrations are mentioned for the different mass transfer operations. Let us see the different concentrations before I go to the mathematical equations. We find that while we were discussing vapor liquid equilibrium, the mole fraction was the typical concentration ratio, typical concentration unit that we were using. We were using the mole fraction in the vapor phase and the mole fraction in the liquid phase. The mole fraction in the vapor phase was denoted by Y, the mole fraction in the liquid phase was denoted by X, and usually we had Txy diagrams, Pxy diagrams and Xy diagrams. Often for absorption, we use the mole ratios, but mole fractions, but more common is the usage of mole ratios. What is a mole ratio? It as I have already mentioned in this table, it is the moles of species I divided by the moles of species free I, isn't it? So, therefore, if I have a total solution where x is the mole fraction, naturally 1 minus x is the mole fraction of solute free system and x is the mole fraction of solute. So, in this particular case, the mole ratio which is denoted by capital X or capital Y, naturally capital Y refers to the vapor phase and capital X refers to the liquid phase. They are given as x by 1 minus x and y is given by y by 1 minus y. The reason for often preferring your mole ratios to mole fractions are that these often lead to linear plots. Y versus x often leads to linear plots as compared to small y versus small x. And once more I will try to emphasize that when we are dealing with gaseous components, then very frequently the concentration unit which we prefer is the partial pressure. So, therefore, partial pressure in the vapor phase or the gas phase is often preferred for absorption, stripping and adsorption as well as leaching. And when we are dealing with liquid phases, say in liquid-liquid extraction or in adsorption of a liquid by a solid, under that condition usually we prefer to use concentration or any particular property related to concentration. And here I would just like to mention that usually the concentration in the solid phase is denoted as small q and the concentration in the liquid phase is denoted by either a small c or a capital C. So, therefore, first thing which is important for you to remember are the different mass transfer operations, and what the different mass transfer operations are concerned with. And the second thing is, for all these mass transfer operations, the separation is guided by phase equilibrium considerations, and these phase equilibrium considerations are obtained from phase diagrams or from mathematical relations relating the different equilibrium properties. And these particular phase diagrams, they are denoted either in terms of mole fractions like we have already seen in distillation, or they are denoted, this is one in terms of mole fraction, or they are denoted in mole ratio. The advantage is immediately evident. While we have a curved XY relationship, we have a linear mole ratio relationship. They can also be denoted by partial pressure as a function of mole fraction. This is usually the case for absorption and stripping, where the partial pressure of the gas over the solution is plotted with the equilibrium concentration of the gas in the liquid solution. Here I think this has been plotted as a function of temperature, and as we know, gas solubility decreases with temperature, as a result of which the isotherms they become steeper as we go to higher temperatures. And here this is a typical XY diagram which we have already dealt. This is distillation, this is absorption, and this is also absorption, and this is a typical isotherm for adsorption. Adsorption, we plot, or rather we construct the phase diagrams with the fraction or the amount adsorbed in by the solid phase and the equilibrium concentration of the adsorbate in the remaining gas phase or in the remaining liquid phase. If it is a liquid phase, I repeat, we denote the coordinate with concentration, and if it is a gas phase, we denote it with partial pressure. And this is a typical phase equilibrium diagram for liquid-liquid extraction. We will be discussing, or rather I will be giving some time on it because it is different as we see. Why is it different? Let us understand. When we are dealing with the other mass transfer operations, what do we see? We usually consider that there is only one component which is being transferred from phase A to say phase B. In distillation, it is either from liquid to vapor or vapor to liquid. In absorption, it is from vapor to liquid. Stripping, vapor to liquid to vapor. Adsorption, it is from liquid or gas to solid. Leaching, solid to liquid or gas. But when we are considering liquid extraction, what happens? We find that there is one particular liquid where a component is dissolved. We bring another particular liquid, and although we consider that the two liquids are completely immiscible, in practice we hardly get any liquid pairs which are completely immiscible with one another. So, basically in practice what happens? The solute which has to be extracted, suppose we have A is one particular solvent where the component C is dissolved. We bring B to it such that it extracts C from A. Now, C therefore it dissolves in A, C it dissolves in B, and even if A and B they have got very less mutual solubility, there will be some amount of solubility between A and B. So, therefore, there has to be equilibrium between AC, BC and AB. In order to show all this equilibrium in a single curve, usually we take the help of a ternary equilibrium plot, which I will be explaining after I discuss the other parts. And so, therefore, this is a typical solubility curve for gases in water. Here we find that in this particular case the coordinates are partial pressure of solute in gas as a function of the mole fraction of the solute in liquid, and we find that the steepness of the curves that we get, they denote the extent of solubility. For example, we find that the partial pressure is very high at a low mole fraction for the case of sulfur dioxide, which shows that sulfur dioxide under this particular condition is relatively insoluble in water, while on the other hand the partial pressure is much less at higher mole fraction for HCl solution, which shows that HCl is much more soluble in water. So, therefore, the steepness of the curves gives you an idea of the solubility of that particular component, and from there we know that whether the absorption with this particular solute is going to be feasible or not. If the solubility is very low, then there is no point in using this particular solvent for extracting or absorbing this particular gas. Now, let us go for adsorption. Adsorption, as I have said, it can either be a Q versus C as I have shown here. This is for adsorption of a liquid. We can also have in terms of partial pressure as we have shown here. Now, from this particular curve, it is quite evident that adsorption isotherms, they are called adsorption isotherms because mostly they are plotted at constant pressure. They are not always concave upwards. We can have a wide variety of adsorption isotherms as we can see here. And something very unique to adsorption which I should be mentioning here is that for all other mass transfer processes, see, we can extract the phase equilibrium data either while we are increasing the concentration or while we are decreasing the concentration. And we find that usually for all the cases we get the same equilibrium concentration. For example, in case of absorption, say carbon dioxide being absorbed in water, okay, we can either start with a highly saturated value of carbon dioxide in water, we can keep on changing the pressure so that the solubility keeps on decreasing, and we can record the solubility as a function of pressure or a function of temperature. Or else we can start with pure water, we can keep on dissolving carbon dioxide and increasing the temperature or the pressure and finding out the equilibrium concentration. For both the cases, usually we get the same equilibrium concentration, but this is not the case for adsorption. If we generate the adsorption isotherm during adsorption and during desorption, usually we find that the two curves, they do not coincide with one another, as a result of which there is it exhibits a phenomena of hysteresis, which is mostly exhibited by adsorption and not by other mass transfer processes. And during this exhibition of this phenomena of hysteresis, which is usually exhibited over a particular range of concentration, we always find that the desorption equilibrium pressure is always lower than the adsorption equilibrium pressure. Well, as far as the mathematical equations are concerned, I have already mentioned for absorption it is the Henry's law, and for adsorption the simplest equation is something like the Henry's law. It denotes a linear relationship between the amount which is adsorbed per unit mass of adsorbent and the equilibrium concentration in the liquid phase or the equilibrium partial pressure in the vapor phase. Apart from that, we find that several other equations are available to predict the adsorption isotherms under different conditions. The equations and the special features are mentioned here. It is not important for you to remember all these equations, it is just important for you to remember that since adsorption is so very erratic, as I have shown you the isotherms, as I have shown you the phenomena of hysteresis, therefore, several equations are needed in order to predict adsorption under different conditions. Well, the last thing which I would like to discuss with you is liquid-liquid extraction. In this case, as I have already mentioned, that what happens when we are dealing with liquid vapor cases. The gas phase is always miscible, liquid phase it may be miscible, it may not be miscible. So, therefore, usually a two-dimensional plot of the two equilibrium concentrations under different conditions of temperature and pressure are sufficient to generate an equilibrium plot. But in liquid-liquid equilibrium, as I have mentioned a short while ago, we find that there are mutual solubilities among the different components. Let us take a concrete example. Say we have A where C is dissolved and we add up B in order to, and here what we do, we add up B in order to extract C from A. We know that C is soluble in A and C is soluble in B, right, and also A is soluble to small extent in B and B is soluble to a small extent in A. Now, how to represent such a type of phase diagram? What we do, we usually represent them on an equilateral triangle, where the three apices of the triangle refer to pure components. So, this apex, it refers to pure A, this is pure C, this is pure B, and all the sides of the triangles, they refer to binary solutions. This denotes solution of C in A, this denotes solution of C in B, this denotes the liquid-liquid mixture of A and B. Along this particular side, the relative proportions of A and C is denoted by the particular point where we select. For example, a point here, it has got a small amount of A, a large amount of C, whereas a point here has a small amount of C and a large amount of A. Now, we know C and A form a completely miscible system, C and B form a completely miscible system, A and B their solubilities are very low in one another. So, therefore, they form two immiscible systems which are denoted by point L and point K. If the systems are highly immiscible, points L and points K, they shift more and more towards A and towards B. So, therefore, this particular range, it shows the extent of miscibility of A and B. And we find that between L and K, there is a dome. What does it represent? This particular side from L to P, it denotes that A and B, they are mutually insoluble, and with the addition of C, the change in the mutual solubilities of A and B are denoted by this particular dome. So, within this region, it is a heterogeneous region comprising of two phases. Outside this region, it is a single phase liquid solution. and solubility of C in A and the solubility of C in B, both of them they meet at a point P, which is known as the plate point. And within this particular dome, any particular point, say point M, it comprises of two liquid phases. One liquid phase comprises of solution of C in A and the other liquid phase comprises of a solution of C in B. The compositions of the two phases are denoted by the tie lines which pass through N and intersect this particular dome. So, therefore, at M, in reality we have a solution of A and C corresponding to composition R and a solution of C in B corresponding to a composition E. And we find that all these tie lines, they are usually not parallel to one another, they are usually not horizontal, they gradually change their slope, but the sign of the slope more or less remains the same. There are few cases where we see that the sign of the slope changes and we find that the slope gradually from negative slope it becomes horizontal and then it becomes slightly on the other side. Such systems are known as solutropic systems, but these systems are not very common in one another. So, therefore, we find that in this particular case, if we find the solution of C in E is C in B is much richer as compared to the solution of C in A. This is also denoted by this particular phase diagram, which automatically suggests that B has got a higher, or rather C has got a higher affinity for B, and therefore, B can serve as a proper solvent for extracting C from A. And again, another thing I would like to mention, that any point inside the triangle, we can know the proportions of A, B and C here. How can we know it? We know that the sum of the perpendiculars dropped from this point on the three sides, they equal to the sum of the altitude. So, what do? We assume that the altitude is 100%. So, therefore, these three they sum up to 100% and the perpendicular distance dropped from M on AC, it represents the mole fraction or the fraction of B. The perpendicular which has been dropped from M on BC represents the mole fraction of A and the perpendicular of M from AB represents the mole fraction of C. So, accordingly by this process we can find out for any particular point inside the triangle the composition of the liquid mixture corresponding to that point. When it is inside the triangle, it comprises of all the three components. When it is along the sides of the triangle, it comprises of two components, and when it forms any particular apex of the triangle, it refers to that particular pure component. So, therefore, this completes our discussions on phase equilibrium thermodynamics. We have not only dealt with vapor liquid equilibrium, but also other equilibrium considerations which are important for other mass transfer operations which you will be covering in the course of your chemical engineering curriculum. From here we could understand how phase equilibrium is important for all mass transfer operations and in what way phase equilibrium relationships or phase equilibrium diagrams should be represented for different mass transfer operations. And it is also important to remember that the units in which we express the phase diagrams, they are also different for different systems that we consider. Usually mole fractions are used or preferred, mole ratios are preferred to obtain linear phase equilibrium curves, and partial pressure is a much more relevant unit when gas phase is concerned, just because it is easier to measure partial pressure or the pressure as compared to concentration. For any liquid phase involved or for any solid phase involved, it is the concentration which is important. Usually concentration is denoted by C in the liquid phase and by Q in the solid phase. And it is also important to remember that in adsorption equilibrium isotherms, they are often marked by the phenomena of hysteresis, and therefore, adsorption isotherms, they are comparatively difficult to obtain, and they are mainly based on experimental data and several curve fitting of experimental data as have been proposed by the different adsorption isotherms that we have discussed. And such ternary equilibrium plots, they are not only common in liquid-liquid equilibrium data, they can also be common for adsorption or other mass transfer operations when more than one particular component gets transferred, or in other words, when all the components involved with one another get transferred into one another. But usually the ternary plot is much more relevant for liquid-liquid extraction processes. So, with this I wish you good luck, and I really hope that you have enjoyed the journey of phase equilibrium thermodynamics. We have been solving your doubts and your queries, and we are there for addressing further doubts that you have before your exams. So, good luck and good day to all of you.